Hi everyone, this is a look at an example of a voltaic cell. I have my stylized picture here. Any type of voltaic cell could be represented with this kind of a diagram. Questions occasionally will ask us to draw one, but pretty much we'll always have a picture to interpret. Here I have the cell notation. It's for a standard zinc copper voltaic cell. I have this notation. So my first step is to just put some labels on my actual diagram here. It's zinc solid. That's letting me know that piece of metal out there is zinc solid. And then the zinc ions are in solution down here. I'm going to put two of them. There's probably some nitrate that's also present in there. Even though it's not included in the notation, it's likely that there was some kind of anion in there acting as a spectator. We have the salt bridge. Remember, that's going to be an ionic solution here in this upside down U-shaped piece of glass. A typical example of a salt bridge is sodium nitrate. Sodium nitrate in there, an ionic solution. Then on the other side of the salt bridge, I have copper 2 ions. They're here in solution. Okay, I'm going to put 2 of them, and there's also going to be some nitrates in there. And then this piece of metal on the right-hand side are copper solid. So one of the first things to do is just wrap our heads around what this notation means and how it relates back and forth between the diagram and the notation. The list is here in the notation. I don't need to go through and say, oh, what's present, all that. This is going to act like our list. Technically, there's also water present here, which is not included in the notation, and that's okay. What I need to do is find the strongest oxidizing agent, find the strongest reducing agent. It's been a while, but we have this table in the data booklet. Good rule of thumb, the 2 electrodes on the outside are reducing agents, and the ions in the middle are oxidizing agents. Because this is the standard kind of notation that we're going to see, we're always going to have solids. We're going to always have our 2 reducing agents on the 2 outside parts of the notation. Now, out of the 2 reducing agents, which one is the strongest? Which one is lowest down in the table, copper or zinc? It's the zinc. It is the strongest reducing agent. That automatically means that the copper 2+ ions here must be the strongest oxidizing agent, or when I use the data booklet, I can find, oh, the copper ions are higher up on the table than the zinc. They're the strongest oxidizing agent. Now, depending on what the question asks, maybe this is only as far as we have to go. But because this is a big example, I'm going to talk about everything that's possible. Okay? The strongest oxidizing agent, the oxidizing agent gets reduced. The half reaction is here in the table. I'm going to copy it down. The copper 2 ions are getting reduced into copper solid. That reduction half reaction is undergone by the strongest oxidizing agent. The strongest reducing agent is going to be oxidized. That's where we take the half reaction from the data booklet and copy it down in reverse. Zinc solid being oxidized into zinc ions and 2 electrons. At this point, I'm able to identify the electrodes, which one is the anode, which one is the cathode. The strongest reducing agent gets oxidized at the anode. So the reducing agent, this is going to be the anode. And the anode is that negative electrode. The oxidizing agent gets reduced, and reduction occurs at the cathode. So the copper electrode over here is the positive cathode. Okay. We have the half reaction that's taking place at the cathode. We have the half reaction for the anode. We're able to find that net reaction by balancing the electrons. Here the electrons are already balanced, so I don't need to do anything to them. To come up with the net cell reaction. We have the two half reactions. The electrons happen to work out to already be balanced, so we don't need to do any extra work. The electrons are going to cancel. We end up with the net cell reaction. This is a spontaneous reaction, which is an important thing to highlight. Voltaic cells, because they take chemical potential energy and turn it into a voltage, are always going to be spontaneous reactions. Let's say that again, voltaic cells are always spontaneous. When I look closely now at the reactions, the half reaction, and the diagram, let's dig a little bit deeper. Look at what's happening here. The copper ions are going to gain electrons to make more copper solid. As time goes by, the copper ions are going to get converted into copper solid. The ions that were in the solution are going to turn solid. On the other side, on the zinc side, we have the zinc solid being oxidized to produce more zinc ions and 2 electrons. As soon as we hook this up, the reaction starts. It's a spontaneous reaction. It starts immediately. And what happens? The zinc gets oxidized. So 1 atom of zinc solid gets oxidized. It turns into, see how I erased some of the electrode? And a zinc ion showed up in solution. We used up a solid, turned it into an ion, and that freed up 2 electrons. Where do those 2 electrons go? They go through the wire to the copper side. And what do they do when they get to the other side? They get together with a copper ion. The 2 electrons come down, they take out a copper ion and make a copper solid. Here I'm adding on to the electrode. So as time goes by, the concentration of ions in the anode half cell increases. The mass of the solid electrode on the anode side decreases. On the cathode side, the concentration of ions in solution goes down, and the mass of the electrode goes up. In addition, we can see that the electrons were moving from the anode to the cathode. The electrons here moving through the wire are going in this direction, from the zinc to the copper half cell. We can think about the movement of the electrons in a couple of different ways. We could think about, electrons are negatively charged, and if this is the negative electrode, they're being repelled from there and attracted to the positive electrode. That will help us determine the direction of the electron flow. In addition, if we look at the half reactions, we see that the copper side is gaining electrons and the zinc side is losing electrons. So we can determine the flow, the direction of the electron movement, if we examine the half reactions, or if we think about what's going on with the polarity of the electrodes. The final thing that we can do here is calculate how much voltage is this actually producing. And we have this formula, the net cell potential, the voltage. It's the cathode minus the anode. The cathode, which we've been talking about, is this copper. I have to go to the data booklet to find this half reaction. What's that line? I found it up here. It's at positive 0.40. Now I'm going to subtract the anode. The anode is the zinc. So I'm not going to do anything. I'm going to use these numbers. I just got to find that line. The zinc line here is at negative 0.76. So subtract negative 0.76 volts. I can really take my time. This is not an amazing operation, but I can make sure I get it right. 0.4 subtract negative 0.76 is 1.16 volts. A couple of things about this voltage. It has to be a positive answer. If you accidentally get a negative answer, it means you have your anode and cathode mixed up or made a mistake. Because this is a spontaneous reaction that produces electricity, we must have a positive answer here for the voltage, for the net cell potential. Looking back at all of this, this is a general picture. We can take the notation and put labels into our diagram. Okay. The notation acts as our list, where we're going to have the two reducing agents on the outside, and the one that's lower down on the table is the strongest one. The strongest reducing agent is oxidized at the anode. The strongest oxidizing agent is the one that's higher up on the table, and it gets reduced at the cathode. Electrons are always going to flow from the anode to the cathode, repelled from the negative electrode, attracted to the positive one, or gained and lost. Because of what's going on with the reactions themselves, at the anode, the concentration of ions goes up, the mass of the electrode itself goes down. On the cathode side, the other way around, the concentration of ions in solution goes down, and the mass of the electrode goes up. We can do a small mathematical operation using some values that we pull out of the data booklet to calculate the voltage, the net cell potential of this electrochemical cell. And the last thing is there's going to be some movement of ions here in the salt bridge and even these remaining ions in solution. Here it's that the anions, whether they're in the salt bridge or in the solutions, in the electrolytic solutions, the anions move to the anode. So here I'm just going to write the word anions, and they're going to move to the anode this side over here. The anions are going that direction. Cations, the positive ions in the salt bridge or even in the solutions are going to migrate towards the cathode, which on this example is the copper half cell. There's a lot going on in these kinds of questions, but if we take it step by step and we don't rush, we can get to where we need to be. And I hope that helps.